Okay, so I'm holding here one of the Origin optical fiber sensor prototypes, and for the purposes of the demonstration we've stripped some of the protective jacket from this fiber to expose the bare optical fiber here at the tip itself. It's 0.5 millimeters in diameter, which is really a crucial aspect for ensuring that it's able to be inserted into needles and applicators during a brachytherapy procedure to allow for in vivo dosimetry measurements. And what you can also see here right at the tip of the fiber is our scintillator material. The specific geometry that we've employed was designed to ensure that we optimize the amount of light which is coupled into the fiber itself. I've just also set up here on the side, we have one of our optical fiber sensors which has now been inserted into a clinical needle. And there's a locking mechanism here at the top which ensures that once the fibre is fully inserted, it can be locked into place and then won't move during a treatment procedure. When exposed to radiation, light will be emitted by the scintillator tip, which will propagate along the fibre and then travel to our detector system. So here we have a rack of 16 silicon photomultipliers. I've only connected one fibre here at the moment. But the Origin system crucially will have that ability to consider up to 16 optical fibres at a time, so we can sample many different regions of interest during a brachytherapy procedure. As I said previously, the silicon photomultipliers that are stored in here are what we're using to count the number of photons which are emitted. They have excellent sensitivity, excellent photon detection efficiency, and small size, which, as you can see, when you consider 16 of them, the small size becomes a crucial factor in making sure that this is a portable device that could easily be integrated into a clinical environment. The fact that the Origin system allows for up to 16 optical fibres to be employed clinically means that we can measure the dose at various clinically relevant regions within a patient. Now, the Origin system itself is primarily focused on prostate and gynecological cancers. So our organs at risk, which we're interested in assessing the dose to, are typically the rectum, the urethra, possibly the bladder. And we also want to sample dose in the high dose region areas to ensure that we're getting that uniform dose distribution to ultimately achieve the goal of our brachytherapy procedure.
The Work Package 2 has the aim to develop a 16-channel system for the Origin project. Now I'm going to explain you in the detail the system. The scintillator material is a material that, when it is irradiated, emits light. The light, it propagates along the optical fiber, and the light from the optical fiber is read out by a silicon photomultiplier, a small sensor that is able to detect photons at the level of the single photon. Inside that board there are 16 silicon photomultiplier, and we are planned to connect 16 fiber at the silicon photomultipliers. In the standard brachytherapy treatment, the fiber were inserted inside the body, or with a needle like that one, or with a catheter like that one. Instead, in the lab, to qualify and test the board and the fiber, we use an X-ray tube. The X-ray tube is able to produce X-ray at different intensity. The 16 fibers were inserted inside the X-ray tube through a duct, and they were connected to the board. The signal from the silicon photomultiplier is read by another board, that is the board developed by a company in collaboration with the university. Here there is the software to read out the data from the board, and you can see the noise level of the sensor that is always present. If I'm going to switch on the X-ray tube, the sensor is irradiated and the lights propagate until the silicon photomultiplier, the signal is read out, and you can see an increasement of the rate due to the dose that comes on the fibers.
Okay, so what we have here is another key component of the overall Origin system. This is an example of our electromagnetic tracking system. And we have two different options here for your electromagnetic field generator. This particular one here, which is mounted on an arm on the side of the bed, is called the planar field generator, and it will be positioned over the abdominal region of a patient for a typical low dose rate prostate brachytherapy procedure, or indeed a high dose rate gynecological procedure. Also shown here on the patient couch, we have the tabletop generator. And as the name suggests, this one will be positioned underneath the patient, directly on top of the treatment couch. But the concept is the same for both of these field generators. They generate an electromagnetic field, and then we can use our electromagnetic sensor, which when positioned in the field will allow us to determine its precise location in three-dimensional space. And this works through the process of mutual induction. So if I introduce this sensor into the field here, we should be able to see on the laptop screen that we can see the position of the sensor updating in real time as it's moved throughout the measurement volume of our planar field generator. The key component or the key value in this component is that it will allow us to precisely determine the position of individual optical fiber sensors. And when we know precisely where those sensors are in space, it enables us to determine where the source is in space. So this really is a crucial step in the overall Origin system. Okay, so what we have here is an example of a 3D printed anthropomorphic phantom, which has been developed as part of the Origin project. This is a phantom which is designed to mimic the properties of the human body, and the specific geometries within the phantom are derived from a CT dataset. Now, this is very useful within the Origin project because it gives us the opportunity to characterize and test the Origin prototype sensors in a more complex and clinically relevant environment. Okay, so this phantom has also been designed using kind of a modular concept so that we can swap out components, which gives us the flexibility to consider a wider range of patient geometries. You'll also see here that the phantom has been designed to incorporate a Foley catheter, for example. We have needle catheters, and we also have the ability to introduce an ultrasound probe into the phantom to better replicate the clinical environment.